Hello everyone. I want to just take a moment here to go ahead and introduce you to an exercise that's going to walk you through the process of normalization. And this is going to be all wrapped around an example utilizing a puppy kennel. So I think first and foremost we want to understand what a puppy kennel is. This is a location where a dog or a pet owner can take their animal and the people will watch it for them while they're either gone away for work or for a vacation and they simply can't take their animal with them. So the scenario that we have here is there was a manual system that the owners of the kennel were using, and the manual system was starting to give them limited information in order for them to grow the business. So they were tracking all kinds of unnormalized data. So this is nothing more than a flat file that kept track of all these kinds of different data points. And really, for them to grow the business, if they wanted to go in and analyze this data, they would have to pull all these manual files, so a paper file system, and then start doing some hand tabulation of types of dogs, and also they keep track of the types of tricks that they learn while they're at this particular kennel, or the types of tricks they know already when they come into the kennel. So they were trying to figure out, like, what's a value-added service, how can they make this a better and more attractive kennel, and so on. But all this data and information ultimately was locked up in this manual system. Ultimately, there's another problem that starts to evolve, and that is the aspect of, can Fifi roll over? So can Fifi roll over? This is asking the question that if they wanted to know if this particular dog can do these tricks, they would have to go in and look it up. And then there's another question a little later on. What if Fifi were to disappear from the kennel? Does that mean also the trick would disappear? There's a lot of drawbacks to manual systems that we've learned over the years. We've been building databases for decades now, and really some of the manual the drawbacks of the manual system simply could be fire, could destroy the paper, and if you don't have a backup copy located off-site, you could have all your files destroyed. If you live in a location where you have floods, you could also see the paper destroyed in the flooding and so on. And ultimately, it is a manually intensive process. So over the years, as you gather more customers, you're generating more paper. So now when you got to go and look up information or make use of all this information you've collected, it's just an incredibly time-consuming task. So, give you an idea now, this is a database form, or actually the paper form that the owners would provide to the pet owner. So when the pet owner would show up, they would have them fill out this form. And this is a real simple form, but they would ask things like, what is the puppy's name, of course, and then the owner's name and all this other stuff, but puppy name. And then they would also keep track of, where they were going to store the actual animal while the owner was gone away. So this all becomes really important. And then they would store it, in a manual file and cabinet system. So what we're going to do here is take a look at this unnormalized data, and we're going to normalize it. And that's a process. In order for us to get it into a form that we could then implement it in a relational database design. So what we start to see is we want to ensure the database has all the required data. That's a normalization goal, along with reducing redundancy and allowing for efficient updates, and most importantly, not losing any data. So the one thing I want to comment on is redundancy. We live in a day and age now where we find storage is becoming cheaper and it's much more accessible. And then we also have the cloud on top of everything else now, where we once used to worry about servers with hard drives, now we can push it out to cloud storage and whatnot. But the problem still exists where if we're storing unnecessary data redundantly, meaning we're keeping duplicate data, we're also creating possible performance issues in our system as it starts to look for information. And then also we want to make sure that it is efficient and it is a well-tuned application. So when we say allow for efficient updates, when the software application starts to interact with our database, we want to make sure that it's responsive. A lot of times you'll make a phone call, you'll be talking to an insurance company or some other organization that has your information in their database systems, and they'll start to talk about how, oh, the system is running slow today. Well, that may be the case, of a network problem, but it might also allude to a bad design in their database. And then last but not least, when we're doing all this, we want to make sure that as we strive to build this relational model, that the entities that we create start to contain the data that helps describe those particular entities. And we're really looking for tables with a theme. So if we have a puppy table, we will ultimately have only puppy information in that. Much like a business has an employee database, they might have an employee table. Well, you're not going to see inventory information in the employee table. So moving along, we start to realize that when we're building our systems, we sometimes encounter certain anomalies. So before we even begin this process, we start to recognize the fact that we might have an insertion anomaly, which is basically saying when you go to put the data into your structure, it may not be placed in the right location. And then the contrary to that, or the opposite of that, would be the deletion of that. So these two anomalies exist right off the bat whenever we're working with our data. So the first step here, and this is a process, right? So there's a series of steps that go along with this. The first step is to eliminate what are known as repeating groups, to try to identify them. Once you identify repeating groups, you can actually extract those attributes from that particular entity and then put it into its own separate entity, assigning it a primary key. So at first glance, we start to see that we could break the unnormalized list that we saw in the prior slide, and we could create actually a puppy table, and that puppy table will have a primary key, and it'll have some additional attributes. We'll then see a second table evolve, and that will contain the trick that the puppy might know. Well, in order to help track this, we'll see that we'll also bring along the puppy's number, a trick ID, and then what the trick is, and then we're also going to keep track of where they might have learned it, and we'll assess a skill level from, say, 1 to 10. Now, one of the great things about this particular exercise is the fact that you'll see that the names really are helpful. These attribute names are awfully supportive in having us understand the dependencies that exist. So you look at just the names alone. Now, you may not always have that luxury, though, when you're building your database systems. A lot of names or attributes can be quite cryptic. So you'll have to work with a liaison of some sort who's going to help you define what these attributes truly mean so you can understand what the dependencies are. So this is a very good start, but it's quite not where we want to be. Now, what we start to see here is a little bit of SQL, you know. So we see the table dot attribute or table dot column nomenclature, and we see that puppy number equals or puppy number equals trick.puppy number. We try to create somewhat of a relationship between these two. Now that's just purely for example. We're not really going to be doing anything with that. And if you have never done any SQL yet where you're working at this level, don't worry about it. It's really not needed for the rest of this exercise. But I do bring it to light so you can start to see why we establish these keys. Now, I do want to show you an example here, but I always hesitate when I show this type of work because you have to look at the data and you really don't want to look at the data. So in any case, here would be the trick table with its attributes, you know, trick, puppy number, trick ID, trick name, and so on. And then we could populate it with some sample data. Okay. Now, as you can see, we have the puppy appearing here, and each one of these puppies has a trick. All right. So notice that trick ID, though, does repeat. Puppy number at this point does not. In the trick table, we start to realize that we have to take and combine the puppy number and the trick ID together in order to uniquely determine these other attributes. Well, one thing that starts to appear, though, is the fact that trick name is only partially dependent upon the key. So trick ID determines trick name. Puppy number does not. So when we start to encounter this is known as a multi-valued key, right? This is a composite primary key, a multi-valued key. And when an attribute is only partially dependent upon part of the key, the composite key, then it's a candidate to be removed and put into its own table. So once again, we reiterate that and we start to see that there's a partial dependency with that all. So that takes us to rule number 2, eliminating redundant data. If an attribute depends on only part of a multi-valued key, remove it to a separate table. Anomalies still exist at this level, and they're the update and the deletion anomalies. The bottom line is you're going into multiple places trying to do multiple updates instead of doing it like in one-stop shopping. And as far as the deletion anomaly goes, in that particular table right now, as it sits, if one of the dogs were to be run over by a truck, I'm sorry to say that, I mean, I'm a dog lover myself, but the thing is, will that trick be deleted such that no one else could have that trick? So now we move that to second normal form. In doing that, we could start to further break them out and looking at the rule and evaluating the dependencies. We can now see a puppy table emerging, a trick table with a trick ID and a trick name, and a puppy trick table that will keep track where they learned it and a skill level. What we start to do though is we separate it for those depending only on the trick ID. So we're always looking at the tables, or excuse me, the entities. We're always trying to understand what are these dependencies, what are the partial dependencies. It's an iterative process. You keep on scrubbing your entities until you break them down. So we now see these two new tables. Here it is on a little bit higher level, so if you weren't able to follow that along, we went from these sets of tables, or entities, I better say, over to these entities. First normal form to second normal form. So now we still need to strive to the third normal form, and we'll apply rule number 3. Simply eliminate the columns that do not depend on any key. So if we start to find out that there's an attribute hanging out in that entity that really has no role and it has no relations or dependencies with any of the other attributes, move them completely out. So we start to see the puppy table would be a really good candidate for that. And I think you could see just by the names alone what I'm going to get ready to do here. All right, so now we start to see that we're going to move this to third normal form. It does satisfy first normal form because there's no repeating group. It does satisfy second normal form because there's no partial dependencies. And this is where we land. Since the key is puppy number and the kennel attributes describe a kennel, not a puppy, we break them out. We now see it move to third normal form, and we have arrived. So these are the resulting 4 entities that evolve from that one flat file at the very beginning. So what I thought we could do here is take a little bit further look here. This is what the flat file would probably look like if we were to visit the puppy kennel. before they began the process of building their database. You can see that, of course, these column names are more database-oriented column names, puppy ID, puppy name, but you get the idea that the owner would actually be able to track this stuff. And, you know, as they were looking at their manual forms, they would take the data out of the manual form off the piece of paper, and then they would go over to maybe a spreadsheet tool like this, and then they would begin to type it in here. Now, this is just a handful of records. Over 10, 15, or 20 years that the kennels existed, we would start to see maybe hundreds, if not thousands of records, and that once again becomes really hard to manage, and a database really looks like a good idea at that point. But you'll notice that that Fifi appears more than one time, right? And immediately you might say, oh, that's got to be a mistake. Well, no, because the way the flat file is organized, we have to have 3 separate entries because Fifi is a quite talented dog. It actually knows how to sit, roll over, and speak. So in the way this is set up, we have to actually enter it 3 separate times. And it's not just with Fifi. Shemi also has some multiple occurrences, and that's where this all starts to have the anomalies and so on. So if we were to take the normalized model that we just came with, we could actually implement it utilizing Microsoft Access as an example. And the ERD, the entity relationship diagram, would look something like this. You'll see that we have the kennel table, we have the puppy table, a puppy trick table, and a trick name. Now, one of the things I do want to discuss is the relationship that exists here. What we have implemented in this design is a one-to-many design. And it kind of ripples through here. The one area, though, that is not indicated very clearly, because it's access, is the aspect of the foreign key. So the gold key here in each of these entities represents the primary key. In the puppy trick table, though, we notice that we have 2, and that's known as a composite primary key. And I'll talk about that relationship here in a moment. But you'll notice that in this particular implementation, in the one-to-many, on the one side, we will see it's the primary key, and on the many side, it's related to the foreign key. Now, referential integrity rules are those that start to maintain the integrity of your database design, and that particular rule states that the foreign key cannot exist without a corresponding primary key. Excuse me. So we have to make sure that when we're populating the data in our tables, we have to make sure that the primary key has its value, and the foreign key then also can be populated once it's populated in here, because the values will be matching. Now, excuse me again. The one other area that I wanted to just talk about real briefly is this over here. If you were to say, what is the relationship between puppy and trick? You could say, well, a puppy can know one or many tricks. And then a trick, well, a trick doesn't always just belong to one and only one puppy. A trick can actually be learned by many puppies. So that relationship between puppy and trick is actually a one-to-many. Sorry for the bad handwriting, which is indicated as, I'm sorry, I said one-to-many. It's a many-to-many relationship. Whenever you start to encounter a many-to-many relationship, you'll see the creation of an intersection table. And that intersection table will have a primary key that's a composite primary key, and at a minimum, it will pull the primary key from the left table and the primary key from the right table. And that's how you get its primary key. So it's a composite key. It could have a third key involved there, depending upon the design. But for the most part, you'll see that. And it is indicated here. If you notice, it's a one-to-many and a one-to-many, hence the many-to-many. I'm hoping that showing this example demonstrates how you can take a flat file, go through the normalization process, and then ultimately result in a database design that will serve your needs and avoid any types of redundancy.